Right, and in this video we're going to talk about the other kind of infinite limit. This is the one where we look at the limit of a function as x goes to positive infinity. And we're going to illustrate this with an example. We're going to do the limit, we're going to show the limit as x goes to infinity of e to the minus x equals 0. Okay, that's what we're going to try and do. So with these, when we're working with a formal definition like this, one thing we got to notice, we need to know what the value of the limit is already. Okay, so we need to know that we're trying to show that the limit is 0, not find what it is. And then we just got to understand what the formal definition means. So in this case, what we have is a similar kind of statement from other limit statements. The limit as x goes to infinity of our function is equal to a number b, which we need to know, if for every positive epsilon there exists a corresponding m. Okay, again, whenever you've got these formal definitions, for each something there exists something else. Often, in fact normally, that something else, the m in this case, is going to depend on what epsilon is. Okay, so for a really loose value of epsilon, a really big value, m might be quite small, but as epsilon tightens up, m could be quite big. We'll show you that in a second. Such that the difference between f of x and b, okay, so the distance of f of x to b for everything greater than m is less than epsilon. So again, we'll illustrate it with reference to our example. So here's our graph. E to the negative x just looks something like this. That would be 1. And eventually it's going to tail off towards 0. So what does our function, what does our definition mean in this context? Well, if we specify a value of epsilon, so let's specify epsilon here. Okay, there exists an m greater than 0 such that, okay, so b in our example is 0. So we want to look at the interval b plus epsilon to b minus epsilon. So you can think of this as b plus epsilon and b minus epsilon, where b equals 0. Okay, so here's our band, and again we'll draw some imaginary lines across. So no matter what value of epsilon I specify, I want to be able to find a value of m such that, okay, so let's specify one here, so that if I go to the right of that, my function is inside this envelope here. Okay, and you notice that you can see that if I tighten this boundary down, if I make epsilon say here and here, I'm going to have to go further to the right to guarantee that everything to the right of m is going to be within that boundary. Okay, so that's how the definition works. So to solve the problem, to lay it out, we're going to say, well, for each, so example, let's just lay it out in full. Example, show that limit as x tends to infinity of e to the minus x is equal to 0. So if we just translate the definition, for each epsilon greater than 0, we need to find an m such that the absolute value of our function, which is e to the minus x, minus b, which for us is 0, is less than epsilon for all x in our domain. Now our domain is the entire set of real numbers, so I won't worry about that, satisfying x greater than m. Okay, that's what we need to find. We need to find an m for which that is true given a particular epsilon. Okay, so let's have a go. So again, we can start from the inequality and see if we can use this to derive an m that depends on epsilon somehow. So our inequality is e to the minus x is less than epsilon, as e to the minus x is greater than 0. Now notice that exponential is always positive, so we're allowed to take natural log of it, and because log is an increasing function, it's not going to affect our inequality at all. So we're going to get, taking logs of both sides, we'll get we'll get negative x is less than natural log of epsilon. Multiplying through by negative 1, we get x is greater than negative log of epsilon. Okay, and so now what we've found is that if our function is less than epsilon as we require, that is equivalent to saying that x is greater than negative log of epsilon. Okay, remember epsilon is a specified positive number, so we're allowed to do that. Alright, so negative log of epsilon is therefore a suitable choice for our m. Okay. Okay, so given epsilon, if I set m equal to negative log of epsilon, that guarantees that e to the x is going to be between, well, it's going to be less than epsilon for all x greater than m, or greater than negative log epsilon. And hence, we have shown, using the formal definition, that the limit as x goes to infinity of e to the minus x equals 0.